So now that we have learned Gauss's law, let us see if we can apply this and get somewhere. So first, let me consider a cubic volume. A cubical surface which encloses a point P. The point P is at the center of the cube. P at XYZ has a flux density D naught. The three components dx naught, dy naught, and dz naught. Now, by Gauss's law, the surface integral of d dot ds, which is the total flux cutting the surface, total surface, must be equal to the total charge enclosed, which is q. Now, if I need to take the total surface integral, what I need to do is I need to find the flux density at each of the faces of this cube and compute the surface integral of that. So let us consider first the front face, which is perpendicular to the x-axis. What would be the flux density? We are going to assume that the flux density is uniform over each face. So what would be the flux density on the front face? Let us say that is dx front. Dx front is equal to dx naught. Dx naught is the flux density at point P plus delta x by 2, that is the distance of the front face from the point P, into the rate of change of dx with x. This can be written as dx naught plus del x by 2 del dx del x. Similarly, if I now want to find the flux density on the opposite face, which is the back face, this will be again dx naught minus del x by 2 minus del dx del x, because it's in the negative direction, which brings me to the same quantity dx naught plus del x by 2 del dx del x. Now, if this dx front is the flux density on the front face, what is the total flux on the front face? This is dx front into delta y into delta z, which is the area of the front face, delta y into delta z. So therefore, the total of the flux cutting the front and the back face would be del dx del x into del x del y del z. Similarly, we can find the combination contribution from the left and right faces and the top and bottom faces. Left and right faces would have a del y variation, and the top and bottom faces would have a del z variation. So now I take integral over the entire 6 faces, which brings me to this quantity. This quantity within bracket multiplied by delta x, delta y into delta z. What is delta x, delta y, delta z? This is nothing but the volume of the cube. So therefore, I replace this with volume delta v. So this integral d dot ds is equal to the charge enclosed. The charge enclosed in volume delta v is equal to this quantity into volume delta v. The total charge enclosed in volume delta v would be the volume integral of the charge density rho v. So integral rho v dv. Therefore, this quantity within brackets is equal to the surface integral divided by delta v in the limit delta v tending to 0, which would be equal to the volume charge density rho v, because charge enclosed divided by volume is rho v in the limit delta v tending to 0. Now, if I look at this quantity in brackets, what does this quantity represent? Mathematically, this represents the divergence of the quantity d at a point. What is divergence? The mathematical definition of divergence of any vector flux density is that it is the outflow of flux from a small enclosed surface per unit volume as the volume shrinks to 0. So what does that mean? Let us consider this figure where you have these flux lines emanating from a point. Let us consider a point here, point P, and let us imagine a unit volume surrounding this point P. In the limit that this volume shrinks to 0, the divergence at point P will tell me what is the outflow of flux from a closed surface enclosing this unit volume in the limit that the volume shrinks to 0. So essentially, divergence tells me how much flux is leaving a particular unit surface. This brings me to Maxwell's first equation. Maxwell's first equation derives from Gauss's law. We have just seen that the surface integral of d dot ds is equal to the total charge enclosed. So integration d dot ds would be equal to the volume integral of rho v rho. So integral of rho v dv, rho v being the volume charge density. And by identity, the surface integral of any vector quantity Can a surface integral of the dot product of any vector quantity can be represented by, can be equated with the volume integral of the divergence of that vector quantity, which is to say that the surface integral of d dot ds is equal to the volume integral of divergence of d dv. Again, the left hand side is also equal to the same volume integral of rho over the same volume dv. Now, if two integrals taken over the same volume are equal, then the integrals must also be equal, the integrands must be equal, and therefore the integrands of this volume integral, divergence of d must be equal to rho. What is this? This is nothing but Gauss's first law. What does Gauss's first law then tell me? Gauss's first law tells me what is the divergence of D, the flux density, the electric flux density D at a point. And it tells me that it should be equal to the charge at that point. The divergence of any vector at any point indicates a source or sink for the flux lines. And for electrostatic fields, the source or sink of flux lines is a charge. A positive charge is a source of flux lines, and negative charge is a sink for flux lines. So by Gauss's law, if I know that divergence of D at a point is 0, it means that at that point there are no charges. And if there is a finite quantity rho, it tells me what is the charge density at that point.